Next we will see the second type of nucleophilic substitution reaction, that is SN1 mechanism. That means the first mechanism through which the alkyl halides can undergo nucleophilic substitution reaction. That is, the first mechanism is SN1. Then there is one more mechanism through which the alkyl halides can undergo nucleophilic substitution reaction, where the X can be replaced by a nucleophile, that is SN1. SN1 means substitution nucleophilic unimolecular. Then why it is known as unimolecular, we will see. So, in order to study the SN1 mechanism, so here I have taken a tertiary halide. For example, tertiary butyl bromide is taken. It is treated with aqueous NaOH. We know that the nucleophile present in aqueous NaOH is OH minus. So, what happens in CH3 thrice Br? Yes, this Br will be replaced by OH. So, we get CH3 thrice COH and Br minus, where this CH3 thrice CBr, it is known as the tertiary butyl bromide, is called as, generally what we can call as, it is an alkyl halide, or we can call it as a substrate. So, that on reaction with a nucleophile, that is OH minus. So, OH minus we can call it as either as a nucleophile or as an attacking reagent. So, attacking reagent will be attacking on the alkyl halide. So, in the first mechanism in SN2, what we studied, the attacking reagent or nucleophile will be attacking from the back side of the leaving group, when at the same time the halogen will be going as X minus. So, here how the mechanism is. Okay, so here after attacking, the X will be replaced by OH. So, we get CH3 thrice COH as the product, and here since the halogen is bromine, the leaving group will be Br minus. So, remember always the leaving group will be X minus. If the halide is chloride, the leaving group will be Cl minus. If the halide is fluoride, the leaving group will be F minus. So, remember always the leaving group will be X minus. Now, as we said in the previous video, in order to write the mechanism of any nucleophilic substitution reaction, whether it is SN1 or SN2, we have to expand the X attached carbon atom only. We need to expand only the X attached carbon atoms. So, if we expand the tertiary butyl bromide, how it will be? Yes, first we have to project the CX bond. So, here it is CBr. Which are the other groups on that carbon? Yes, 3 methyl group, and see how it is represented. It will be present in 3 different planes. Now, so if it is a tertiary, this is a tertiary halide, isn't it? So, if it is a tertiary halide, it will be following SN1. Now, how the SN1 mechanism? Yes, it is taking place as a 2-step mechanism. So, here in SN1, the nucleophilic attack is taking place in 2 steps. How? So, this is the expansion of the tertiary halide. As we know, the CBr bond is polar. So, bromine being more electronegative, it will be getting delta minus, and carbon will be getting delta plus. So, in the first step, what happens here is bromine, that is the halogen, will be going as X minus or Br minus with the bond pair of electrons. In SN1, the time when this halogen is leaving as X minus, at the same time the leaving group is, the nucleophile or the attacking reagent is attacking from the back side. But here, in the first step, the leaving group will go with the bond pair, and only in the second step, the nucleophilic attack will be taking place. In SN2, both the leaving and attacking is taking place simultaneously. So, here the leaving of leaving group is taking place as the first step. So, here when Br is going with the bond pair of electrons, what happens to this carbon? It will get a complete positive charge, isn't it? So, how we can represent it as? So this carbon will be getting a complete positive charge, and we can call it as a carbon carrying positive charge is known as a carbocation is formed. And we know that now in this tertiary halide, the three other groups are on three different planes. But when bromine is leaving as Br minus, so here bromine is going as what? Br minus. So that this carbon gets a positive charge. Carbon carrying positive charge is known as carbocation, and we know that carbocations are always planar in geometry because they are sp2 hybridized. So how we can draw the structure of this remaining carbocation here? Now there is no more bromine here. The three other groups on this carbon atom are 3-methyl groups. So how they are? They are planar. Means all the three groups will be present on same plane. This is the structure of a carbocation. We know that we have already learned in class 11. Carbocations are always sp2 hybridized and planar. Whatever the groups present on the carbon carrying positive charge, they all will be on same plane. So this is the first step happening in SN1 mechanism. So what we can call as the step 1? Yes, it is the formation of carbocation. Step 1 is the formation of carbocation. And remember, step 1 is reversible and it is the slowest step among these two reactions. Not these two reactions. Among step 1 and step 2, step 1 is slow and reversible, and step 1 is the formation of carbocation. So in the first step, X is leaving as X minus. So there is removal of leaving group as X minus, and the second step only the attack of nucleophile will be taking place. So this is the carbocation which is formed in the first step, that is this first step is the slowest step, or we can call it as the step 1 is the rate determining step of SN1. Now in the second step is the nucleophilic attack. And the nucleophile will be attacking on the carbocation formed in the first step. So here the carbocation is planar and sp2 hybridized. So since it is planar in geometry, the nucleophile can attack from either side. It can attack from right side also and from left side also. So how we can write the product as, if the nucleophile, here the nucleophile is what? It is OH minus, isn't it? So here it is reacting with aqueous KOH or NaOH, whatever it is. Here the nucleophile is OH minus. So if the OH minus is attacking from the right side of carbocation, what happens? After the attack of this nucleophile, there is formation of new carbon OH bond, isn't it? So now here the carbon is surrounded by three groups only and it is a carbocation. But after the attack of nucleophile, the hybridization will change to sp3 and the geometry will go back as tetrahedral itself. So if the nucleophile is attacking from right side, where will be the new OH bond, COH bond on right side? What about the other three groups? They will go back to their original position in three different planes. CH3, CH3. So if the nucleophile is attacking from right side, this will be the configuration or the arrangement of atoms in the product. Now on this carbocation, as we said, the nucleophile can attack from either side of the carbocation. Equal possibilities there because it is planar. Now if the nucleophile is attacking from the left side, from this side, how it will be? Carbocation is this, the OH is attacking from this side. So where will be the new COH bond? Yes, on left hand side. and the 3 other groups go back to 3 different planes. Now look at the structure of the products. So in the first step, if we have taken or if we are taking a D-isomer. So in the first step, what is happening in the first step? From the alkyl halide we have taken, halogen will be going as Br minus and there is formation of carbocation. So if the alkyl halide that we are taking is dextrorotatory, see the configuration of dextrorotatory. This is not dextrorotatory. We are assuming if this is dextrorotatory, what happens? Compare the configuration of this alkyl halide with the product. If this is dextrorotatory, this and this will be having same configuration, isn't it? This alkyl halide and this product, if the OH is attacking from the right side, we are getting this product, and this. These two products are having this one and this one, both are having same configuration. So if this compound is dextro, this one also will be dextro. Now if this is dextro, definitely this compound is having just opposite configuration, so we can call it as levo. So in SN1 mechanism, there is equal possibility or equal chance for the attack of nucleophile from either direction. So if it is attacking from right side, if it is dextro, if from left hand side it will be producing levo. Okay, so dextro levo we have to assign based on the alkyl halide we are taking. If the alkyl halide we are taking as L, this will be L, having same configuration. And this mixture, so after SN1 mechanism we are getting 50% D and 50% L4. So this 50:50 mixture of D and L isomers or dextro or levo isomers are known as racemic mixtures. What is meant by dextro and levo? The isomers which can rotate the plane polarized light towards right. Levo means the isomers which can rotate the plane polarized light towards left, isn't it? So 50% dextro and 50% levo means such mixtures are known as racemic mixtures. But these mixtures are optically inactive. Why they are optically inactive? Racemic mixtures are always optically inactive. The reason is the rotation due to one isomer will be cancelled by the rotation due to another isomer, because half will be having clockwise rotation and half will be having anti-clockwise rotation. So the net rotation will be 0. That is why racemic mixtures are optically inactive. Now how we can represent a racemic mixture? They can be represented as DL together or plus or minus in single bracket. So this is the representation of racemic mixtures. Okay, so remember. So what is the main difference between SN1 and SN2 mechanism? In SN1, the leaving of X minus and the attack of nucleophile both are taking place simultaneously. But in SN1, SN1 mechanism is taking place in 2 steps. The step 1 is the formation of carbocation, and how the carbocation is formed when halogen, when it leaves as X minus. And since the carbocation formed is sp2 hybridized and planar in geometry, the nucleophile can attack from either direction, leading to a 50:50 mixture of D and L form called as racemic mixture, which is optically inactive. So step 1 we can call it as formation of carbocation, and step 2 is the nucleophilic attack. And remember, in SN1 mechanism, since it is taking place in 2 steps, one of the step will be the rate determining step. So here the slowest step is step 1, so that is the rate determining step. So in the rate determining step only one reactant molecule is there, that is the alkyl halide present. So that is why it is known as unimolecular reaction. So why SN1 is known as unimolecular reaction? Because the rate determining step is the slowest step, that is a step 1 formation of carbocation. In that step only alkyl halides are present. So here the rate depends only on the concentration of alkyl halide, that is why it is a unimolecular reaction. Now what are the things regarding kinetic data of this reaction? So the rate depends on only on the concentration of alkyl halides, because the step 1 is the slowest step or the rate determining step. So in terms of the tertiary butyl bromide, how we can write? The rate of reaction depends only on the concentration of tertiary butyl bromide. Or if we want to replace the rate proportionality sign, it will be equal to the rate constant K into concentration of alkyl halides. So here remember, in SN1 mechanism the rate depends only on the concentration of alkyl halides, because step 1 is the slowest or the rate determining step. That is why it is a unimolecular reaction. So remember, why SN1 is unimolecular reaction? Because the rate depends only on the concentration of alkyl halide, but in SN2 rate depends on both the concentration of alkyl halides and nucleophile. Now what about the stereochemistry of SN1 mechanism? It is known as racemization. The stereochemistry of SN1 mechanism is racemization. Why? As we explained, the carbocation formed in the slowest step is planar and sp2 hybridized. So the nucleophile can attack from either side, leading to a 50:50 mixture of D and L isomers. And such a mixture is known as racemic mixture, and it is optically inactive. Optically inactive because the rotation due to one isomer or half of the isomer will be cancelled by the rotation due to another half, and it is represented by plus or minus in single bracket or small d and small l together. Remember, racemic mixtures are optically inactive, and the stereochemistry of SN1 mechanism is racemization. Okay, now the order of reactivity of alkyl halides towards SN1. Tertiary halides are more reactive than secondary, than primary and methyl. So methyl halides are least reactive and tertiary halides are more reactive. The reason is, here the rate determining step is step 1, that is the formation of carbocation. We know that tertiary carbocations are more stable than primary and secondary due to hyperconjugation. So higher the stability of carbocation, more will be the rate of reaction in SN1. So in SN1 the order of reactivity depends on stability of carbocation formed in the slowest or the rate determining step. Now we know that the tertiary carbocations are more stable than primary and secondary due to more number of hyperconjugated structures. So since tertiary carbocations are more stable due to hyperconjugation, tertiary halides are more reactive towards SN1. Now there is a very important point coming under SN1, the nature of solvent. In SN1 the solvent used must be polar and protic. Polar means it should be having charge or electronic atoms with different electronegativity. Protic solvents means which is able to donate protons or which can donate H plus ions like water, alcohol, acetic acid, etc. So this is a very important point regarding SN1 mechanism. Remember, the solvent should be polar and protic. Now the first question coming, tertiary halides are more reactive towards SN1. The reason is, in SN1, the order of reactivity depends on the stability of carbocation formed. So, tertiary halides are more reactive due to the high stability of tertiary carbocations. Now, the next question is, the reaction between tertiary alkyl halide and OH minus is unimolecular. Why? Why it is unimolecular? Tertiary alkyl halide and OH minus is there, but the concentration, the rate of reaction in SN1 depends only on the concentration of alkyl halide only. So, that is why it depends only on this tertiary halide concentration, not on OH minus, because in the first step no OH minus participating, OH minus is coming only in the second step. So, here the concentration rate depends only on the concentration of alkyl halide, that is why it is unimolecular. Now, the next question is the very important question, repeated board question, very hot question. Why allylic and benzylic halides are more reactive towards SN1? The reason is, as we know, in SN1 the order of reactivity depends on the stability of carbocation formed during the rate determining or the slowest step, that is step 1. So, allylic and benzylic, we know that the allylic and benzylic carbocations are more stable due to resonance. So, why allylic and benzylic halides are more reactive towards SN1? The reason is due to the extra stability of allylic and benzylic carbocations formed. So, how we can draw the resonance in allylic and benzylic carbocations? So, here what happens, this is an allylic carbocation. So, here in the next step what happens, the double bond will be shifting to here. So, what happens here, CH2 will be getting a positive sign, double will become single, CH, single will become double and the positive charge will be neutralized. So, since there is resonance in allylic carbocation, it is stabilized, so it is more reactive towards SN1. Similarly, in benzylic carbocation also, that is also stabilized due to resonance. So, that is why allylic and benzylic halides are more reactive towards SN1. Now, what about the order of reactivity of halides? With the same alkyl group, if the halogen atom is different, which halides are more reactive? Fluorides, chlorides, bromides or iodides? Yes, just like SN2 mechanism, in SN1 mechanism also iodides are more reactive. The reason is due to larger size of iodine, Ci bond strength is weak, so I minus is a better leaving group. Okay.